So far, we have addressed the issues of IP address lookup and packet classification, and we will now see what are the issues in implementing IP over ATM, and then the proposal of a new technology called multi-protocol label switching as the layer 3 forwarding and routing paradigm. So MPLS is poised to address the traffic engineering challenges which are present in the IP networks, and we will just see what are the difficulties of traffic engineering in an IP networks, how that can be addressed by virtual circuit networks like ATM, then what are the challenges of implementing IP over ATM, and how those challenges have been overcome or addressed by multi-protocol label switching technology. So before actually we look at it, let's look at why internet is so popular. So if you look at this, the internet is popular because of two main reasons. One is the robustness of the routing protocol, and another one is the scalability in the addressing mechanisms. Now, what do we mean by robustness of the routing protocol? Now, robustness of the routing protocol, we mean that if a node or a link fails in an IP network, then the packets can get, so the essentially the routing protocol will discover this topology change and will discover an alternate path, and then the packets can get forwarded onto an alternate link or an alternate path. So in that sense, the internet is robust with respect to the node failures or link failures. The routing protocols adapt to the changes in the topology of the networks. Also, one important thing is that the addressing mechanism that have been used in the internet is not flat addressing, as we had just seen in the previous lectures, that it is an hierarchical addressing, in the sense that an IP address comprises of a network part and a host part, and therefore the intermediate routers, or the core routers need to store the entries corresponding to the network part only, and as a result the internet becomes scalable. By scalable, we mean that the node can come up anywhere in the networks without having it to register with all the nodes in the networks. And as we had seen, that this addressing mechanisms is quite similar to the addressing mechanism that is used for the postal addresses, right? So for example, a house can come up anywhere in the city or in a locality without having it to register with all the post offices in the world, and yet it can receive letters from anywhere in the world. So that is possible because the forwarding of those letters is done first based upon the city, and when the letters comes to the city, then you look at the next level, which is the nearest post office where the letter goes, and after that the letter gets delivered to the respective destinations. So similar philosophy is also followed in the IP forwarding, and that has led to a scalability in the network. However, and that is the reason why technologically, the internet is so popular. Of course, the internet has become also popular because of various applications that it has enabled, but from the technological point of view, also the internet is popular because of the robustness of the routing protocol and the scalability of the IP addressing mechanisms. So what are the problems? So first, as I was talking of internet scalability, in internet, we do the route aggregations, and so the prefix of an address may be used to represent the multiple individual addresses, number one. Number two, we are also using, as we had seen, the classless interdomain routing, which is generalized multi-level hierarchical address, CIDR, that we had already discussed, and routing protocols like OSPF or BGP4, they also enable these aggregations and hierarchy. Now, the routing in the internet is done based on a simple link metric, and which is like the shortest path. So between a source node and a destination node, the routing protocol determines, what is the shortest path between the source and the destination based on very simple link matrix, which is the hop count. Okay, so that the path which is shortest in terms of the number of hops is selected as the best possible path. What is important thing here is that while determining the best possible route from the source to the destination, the congestion conditions on the links or the bandwidths on the link or the available bandwidth on the link is not taken into account. Okay, so while this leads to the simplicity, but as we will see that and scalability, but as we will see shortly that this also leads to some of the problems or challenges in terms of traffic engineering. So what are the bottlenecks that we are looking up now? Because of these hierarchical addresses, because of the hierarchical addresses that have been used in the internet, okay, the IP address lookup is done using what is called as the longest prefix match. Okay, by longest prefix match we mean that in the forwarding database we have actually a lot of address prefixes, and a given IP packet may match several of these prefixes. So we have to select the entry corresponding to the longest match this destination IP address gets. Okay, so we have to select the entry corresponding to that. Now if we had followed the classful IP addressing scheme, that is class A, class B or class C IP addressing scheme, then forwarding was very simple. You need to first determine whether the destination IP address is a class A IP address or a class B IP address or class C IP address. But because of this classless interdomain routing, the forwarding is made little complex in terms of the longest prefix match, and as we had already discussed that this is one of the performance bottleneck in today's internet. So that was a challenge. So although it leads to a lot of scalability in terms of allowing aggregation at arbitrary levels, it also leads to performance bottleneck in terms of the lookup. Then what is the second problem? The second problem is that traffic engineering in IP networks is very difficult. Essentially we are following a hop by hop routing, and that concentrates all the traffic onto the least cost path. Okay, so what does it mean? It means that this is a typical fish problem, and so the situation is something like this, that if we have a network like this where the packets have to go from A to B. Now you can determine that since this has more number of hops, this route, okay, so the packets will get forwarded on this route only. Okay, packet will not be forwarded onto this route because this is considered as the shortest path in terms of the number of hops. Okay, so therefore if we follow the routing protocol which is determining the route based on the shortest number of hops, okay, then all the packets will get forwarded onto this. This link will remain underutilized. Okay, so as a result, as I said, that a traffic engineering in IP networks becomes difficult. Essentially, what we are saying that if a net service provider has alternate routes or path, then what ideally he wants it that in the core network all these links are properly utilized. Okay, so none of the links is underutilized and none of the links should be overutilized or should be congested. Okay, so your traffic should be evenly balanced on all the links, leading to a higher utilization. However, if you are following a routing protocol which forwards the packet, which selects the route based on the shortest number of hops, then you may end up concentrating all the traffic on the shortest path in terms of the number of hops, leading to a difficulties in the traffic engineering. Of course, you can avoid this by making a slight modification to a routing protocol, in the sense that you can change the metric and you can say that a metric is proportional to the congestion conditions in the networks. So, as a result, what may become is that even though this path earlier may be shortest, but as you start forwarding more and more packets onto this path, the links may become congested, and therefore, if we define a link metric proportional to the congestion conditions in the network, then this path may slowly become congested, and then the packets may start getting forwarded onto this path also. Now, the difficulty here is that once a particular path becomes congested and you start forwarding the packets on to the other path, then as a time elapses, the path which was earlier congested, you will find it will slowly become it is slowly getting uncongested, and the path which was where now you are the new path where you are now forwarding the packet, that will slowly start becoming congested. Okay. Now, as it starts becoming congested because of your link metric being proportional to the congestion conditions in the network, now the packets will again start getting forwarded onto the other link. So, as a result, what will happen is that this will lead to oscillations in the routes, or what is called as route flapping. Okay. So, one time this particular route will be declared as the best path. After some time, when it becomes congested, then the other route will be declared as the best path, leading to oscillations in the routing. So, ideally we do not want oscillations in the routing. What we really want is that all the links should be properly utilized. So, what we ideally want is that some traffic, if there is some amount of traffic between A to B, some traffic should get forwarded on this link and some other traffic should get forwarded onto this link, such that both these paths are evenly balanced. Okay. So, that is what our objective is. The third problem is, as we had seen, that the best effort delivery. Okay. Of course, an internet is a best effort network. The network makes every attempt to transmit the packets, but it does not offer any explicit quality of service guarantee. So, this is one of the issues in the best effort internet, and we had seen that we can address this issue by incorporating the QoS mechanisms in the internet. So, now what is the solution that a service provider has? And the solution that a service provider has is that it can use ATM as the backbone solutions. Okay. So, it can deploy ATM or frame relay as the core networks. Okay. So, what are the advantages of having ATM as the backbone or the core networks? Okay. So, first of all, as you know that ATM uses short fixed length packets, which we call them as cells. We have already studied this, and the ATM is based on two fundamental paradigms. One is what is called as label swapping paradigm, and another one is the virtual circuit based switching, actually simplifies the forwarding mechanisms. Okay. So, in the ATM, what you do in the ATM routing, what you do is that before the data transfer begins, you set up a virtual circuit between the source and destination using virtual circuit routing, and after that only the data transfer can become. Of course, this circuit is virtual in the sense that one physical link will be statistically multiplexed with several other traffics. Okay. And each of the virtual circuits may be given certain quality of service attributes. Okay. So, that is essentially the paradigm of the ATM. Now, we also, as you know, as we have already seen, that the VCI and VPI labels can be swapped at the intermediate nodes. We had seen that in our lecture on the ATM, because this leads to an efficient use of the VCI and the VPI's number space. Okay. So, that is why it follows a label swapping paradigm also. So, by using this ATM as the backbone networks, we get several advantages, and one of the biggest advantage is that traffic engineering is considerably simplified. The traffic engineering is considerably simplified. The reason being that these virtual circuits, they are routed based on a routing protocol which can take into account the capacity of each link, and as a result it allows explicit routing. So, what we are saying is that when we select the virtual circuit, between the source and the destination, when we are selecting the virtual circuits between the source and the destination, then we can take into account what are the bandwidth available on each link, what is the buffer capacity available on each link, what are the congestion conditions available on each link, and then set up a virtual circuit between some source and destination, or between one node and other node. So, as a result, the virtual circuit routing protocol can take into account the capacities of each link, and then can decide to route various traffics in such a manner that the entire network is sort of evenly balanced, okay, or is balanced as much as it is possible. Also, the advantage of ATM is that it enables the quality of service guarantees. So, these virtual circuits, okay, have quality of service attributes, and therefore, you can also give the quality of service guarantees in the ATM networks. Okay. So, as a result, we have something like IP over ATM. So, these are all IP routers. They are all situated at the edge of the networks, and as you can see, the core is actually comprising of all these ATM switches. Okay. So, obviously, this is a natural question to ask, that why are we not extending ATM to the desktop, why at all have an IP world or an internet world? The answer to that question is that if I extend the ATM to the desktop, then I have to since ATM gives quality of service guarantees and virtual circuits based routing, I have to then set up a virtual circuit right from the user's desktop up to the destination user's server or his desktop. So, as a result, the number of states that would be required to maintain in the networks would be extremely large, and the complexity of the protocol from the source to the destination will increase sort of enormously. So, therefore, because of these reasons also the ATM did not become popular in the local area networks or as a enterprise wide networks. Also another reason was that the ATM was earlier touted as one of the high speed networks, because when the ATM switch was designed, it started from 155 megabits per second, then it grew to 622 megabits per second, but then soon Ethernet caught up with the speed. Ethernet was already having 100 megabits per second, now we have 1 gigabit Ethernet, and we also have 10 gigabit Ethernet. So, as a result, the relevance of the ATM network as a high speed network dropped down considerably. The relevance of the ATM network as a QoS based networks also dropped down because of practical considerations in terms of required to maintain the large number of states. So, therefore, ATM had this niche applications where it is being used as the core networks. Okay. So, the idea essentially is this, that these packets, so you set up a virtual circuit between one to another ATM switch, and you aggregate the traffic at this ATM switch, and these virtual circuits are essentially used as a trunk path between one ATM switch to another ATM switch. So, in the backbone you are having the ATM based networks, you set up virtual trunks or using some of the explicit routing algorithms or traffic engineering algorithms, so that the service provider can see that the links are evenly balanced and the network is efficiently utilized, and you have these IP routers at the edge of the network. So, basically what we are saying, the core of the network comprises of a virtual circuit based networks, which is an ATM switch, and the edge sort of comprises of an IP based networks. So, as a result, we get the best of both worlds. Because of IP routing having in the edge of the networks, we can live with the scalability of the IP world, and because of its hierarchical addressing and routing, and at the same time the core routing being done based on the virtual circuit, we can enable the traffic engineering solutions also. So, now once we say that we are running an IP networks over this ATM networks. Now, this is what is called as an overlay model, and we need to then address some of the issues that arise in running an IP protocol over an ATM protocols. So, now in this overlay model, there are three solutions that has been proposed. One is of course the classical IP over ATM. Another one is what is called as NHRP or Next Hop Resolution Protocol, and the third one is multi-protocol over ATM or what is called as MPOA. So, we will discuss each of these overlay model. We will see that what are the difficulties or challenges that arise in implementing IP over ATM and how they have been addressed or overcome by the individual protocols, and what are the challenges that are still remaining, and how this new technology, that is the multi-protocol label switching or MPLS, is sort of trying to address these problems or difficulties. Now, in classical IP over ATM, what is done is you have an address resolution mechanisms. Okay. So, basically in classical IP over ATM, address resolution mechanism is required to map between the IP and the ATM address space. Okay. So, this is very similar to the address resolution protocol, ARP protocol, that we use it in the Ethernet. So, the approach of classical IP over ATM is to treat ATM as a link layer. Okay. Just like Ethernet is a link layer or as a MAC layer, the classical IP over ATM takes an approach that you treat ATM as the link layer. Okay. So, if there is an ATM cloud and if you want to forward IP packets, if you determine a path in that, then you treat ATM as a link layer. Now, the ATM cloud that will determine the route or that will forward the packets based on the VCI, VPI number. Okay. But over this network, an IP network has been overlaid, very similar to when you have an Ethernet network over which the IP network has been overlaid. Okay. In the Ethernet network, the forwarding is essentially done based on MAC addresses, or if there are Ethernet switches, then the switching is done by looking at the MAC addresses. So, the same concept here in the ATM cloud, the switching will be done based on VCI or VPI addresses, okay, but over which the IP network has been overlaid. Now, in Ethernet, if you want to do the forwarding, since the forwarding is done based on MAC addresses, you need a mechanism to resolve the IP addresses to the MAC addresses, which is what is called as address resolution protocol or ARP. So, in ARP, the IP addresses are resolved to the MAC addresses. Now, Ethernet, since Ethernet is a broadcast medium, so the ARP works something like this, that if a particular node wants to know the MAC address of the destination node, then what it will do is that it will broadcast an ARP request, okay, asking essentially that I am looking for the MAC address of this destination IP address. Now, since it is a broadcast medium, all the users will receive this request, and the user for whom this query is meant will respond by an ARP response, okay, stating his MAC address to the originating node. Okay. So, as a result, the originating node will come to know of the destination MAC address, okay, and after that it can start sending the packets using that destination MAC address. So, similar thing is required here when we want to resolve the IP addresses to the ATM addresses. However, only the problem is that in the ATM switch it is not a broadcast medium like in the Ethernet. So, therefore, you require some kind of an ATM ARP server. Okay. So, there is an ATM ARP server this ATM ARP server is used to resolve the IP addresses to the ATM addresses. Okay. So, instead of using a instead of broadcasting ARP request which is done in the internet, here what you do is that you have a separate server. Now, you then have essentially independent routing for IP and ATM, and we create what is called as logical IP subnets, logical IP subnet which is called as LIS, and each logical IP subnet will have an ATM ARP server. Okay. And hosts in separate logical IP subnets, they will communicate with routers. Okay. So, the situation is something like this, that you may have you may have an IP cloud, and this is a router, and you may have a separate logical. So, this is a separate logical IP subnet, this is a separate logical IP subnet, and this is a router, and of course, it may be a same ATM cloud, but since this has been identified as separate logical IP subnet and this has been identified as another logical IP subnet, the hosts in logical IP subnet, they will communicate via router, separate router. Now, the disadvantages of this classical IP over ATM approach was that the direct ATM connection, the direct ATM connection between the hosts in separate logical IP subnets are prohibited even if the ATM topology is supportive. So, something like this could have happened, that let us say that here is a router 1 and here is a host, this is C and this is router R. Now, suppose these are on the same ATM cloud. That means, if you assume that the hosts A, B and C and this router R, they are on the same ATM switch, but A and B are one logical IP subnet. So, this is LIS 1 and C is on different logical IP subnet, this is LIS 2. Okay. Now, since we are using independent routing for IP and the ATM, now if host A wants to communicate with host C, then it has to first set up a virtual circuit with the router R, and then this router R sets up another virtual circuits with the host C, and then the data transfer can begin from host A to C. So, you need to set up first a virtual circuit from A to R, and then you need to set up a virtual circuit from R to C, and then only the data transfer can begin. Now, actually, since A and C, they are on the same ATM switch, you could have established a direct virtual circuit from A to C also, but A does not know that C is situated on the same ATM switch. A is talking to C based on the IP address. Okay. Now, when it discovers that this IP address is on a different IP subnet, then as per the IP routing, it needs to communicate through a router only. So, this is the sort of disadvantage, that this is like an overlay model where in the underlying data link, the routing is done based on the ATM virtual circuit, and the at the upper layer the routing is being done on the IP addresses. Now, when there are two IP hosts which wants to communicate with each other, the link layer is comprising of the ATM. So, therefore, they know that they can communicate between themselves by setting up virtual circuits. Okay. Now, since they are on different IP subnets, okay, they need to communicate through the router as per the IP routing. So therefore, they need to first set up a virtual circuit between these routers. Okay. So this is one of the disadvantage, that the direct connections is not possible. This leads to setting up of several virtual circuits, even though you could have set up a direct virtual circuit. Now another disadvantage of course remains, and that is for all the IP over ATM schemes, is that there is a considerable segmentation and reassembly overheads. What does it mean? You have these IP packets. Okay. Now when these IP packets needs to be forwarded over an underlying ATM networks, IP packets could be of variable length packet. These packets needs to be segmented into the 53 bytes ATM packets at the ingress of the network, when the packet is to be forwarded onto the ATM switch, and at the egress, when the packet is again coming from the ATM world to the IP world, the packets have to be reassembled. So this is a significant overhead that is coming up in terms of segmentation and reassembly. So basically, it's like this here. So at this point, when the IP packets have to go to the ATM switch, you need to segment these IP packets into those ATM cells, and in this ATM switch world, actually you are having the ATM cells only, and when these ATM cells needs to be now go out to the internet, you have to sort of reassemble them into the IP packets. So significant overhead is there in terms of segmentation and reassembly. Now some of these disadvantages of the classical IP over ATM were addressed by a modification of this protocol, and which was called as the NHRP, or next hop resolution protocols. So in the next hop resolution protocol, what is done is that there is an inter-alias address resolution mechanisms. Okay. So in NHRP, you can map the destination's IP address to the ATM address. The destination's IP address can be mapped to the ATM address if it resides within the same ATM clouds. Okay. And if it resides outside the ATM cloud, then it maps into the ATM address of the egress routers. Okay. So essentially, in this diagram, what we are saying is that there is a inter-alias address resolution mechanisms. Okay. So once you discover that ATM ARP server discovers that A and C are situated on the same ATM switch, then actually you can set up a direct virtual circuit between A and C also in NHRP. And when you discovered that it is the outside the ATM cloud and it is not on the hosts are not situated on the same ATM clouds, then you will map into the ATM address of the egress routers. So this is the modification to the classical IP over ATM paradigm, which is called as next hop resolution protocol. There is of course a disadvantages of NHRP, and the disadvantage of NHRP is that setting up the separate virtual circuits for each flow is difficult for a large number of flows. You need to you need to of course determine whether the hosts are situated on the same ATM clouds or on the different ATM clouds, and also if the flows are short lived, then setting up this cut through virtual circuits, that instead of following through the router is actually undesirable if there are short lived flows. Okay. So these two are the disadvantage. Of course, the disadvantage that the segmentation and reassembly overheads will be there, that actually continues in the NHRP protocols also. Now one thing is there that whether it is a classical IP over ATM or whether it is a next hop resolution protocol or whether it is a multi protocol over ATM, whatever it may be, there are certain limitations of the overlay paradigm, and those limitations of the overlay paradigm is that this overlay paradigm actually uses complete or partial mesh of virtual circuits. So what does it mean? You know, it's something like this, that if we had if we consider here, now let us say that there are so on this ATM switch cloud. So, if you have an ATM switch, now there are routers attached to it. Now, if I want to send packets from sort of A to B, I need to set up a virtual circuit in this ATM switch. Similarly, I would like to send packets from A to C, I need to set up a virtual circuit. So, if there are n routers connected to this ATM clouds, then I need to make a mesh of n square, order n square virtual circuits, okay, so that each router can transmit packets to any other any other routers. So, the disadvantage, one of the important disadvantage of this overlay paradigm is that you have to go for a complete or partial mesh of virtual circuits. Okay. In fact, the complexity is that if there are n nodes surrounding this ATM cloud, then the complexity of this mesh is order n square. The another disadvantage of that is that normally in an IP world, each router is configured to consider its adjacency with each of its next hop neighbors. Okay. Now, what happens, you have this ATM world, for example, you have this sort of ATM switch. Now, A when it wants to communicate with B, it has set up a virtual circuit through this network. Now, this cloud appears like a black box to A and B. It does not matter really how the packets are finally going to be forwarded into this clouds. As far as the IP router A and the IP router B is concerned, for A, the B is like a next hop node. Okay. It does not really matter whether there were virtual circuits set up from this node to this node and this node, how the packets went. This for A, the B is like a next hop router. For A, C is also like a next hop router, and so on. So, basically for A, all these n routers are actually the next hop routers. Now, what happens, because the A and B are unaware that the packet forwarding is taking place in the underlying network through an ATM switch. They are unaware of this. Okay. Now, what happens is that whenever a topology change or a link fails something, for example, some link fails term here. Okay. Now, because whenever a topology change takes place, the IP routing protocol update this information to their next hop neighbors. Okay. Now, in this case, A, the router A will update, in case of any topology changes, will update the routing information. It will send the routing updates to all the n nodes. Okay. Because it assumes that all the n nodes are actually its next hop neighbors. Okay. So, as a result, the amount of routing information that you are transmitting in the presence of topology change, in fact, it can be shown that can be of the order of n raised to power 4. Okay. You are having a complete or partial mesh of order n square, and the amount of routing information or routing updates that you will send in the presence of topology changes can be of the order of n raised to power 4. So, there is a lot of update packets that will flow through, which could have been simply avoided if the IP routers were aware of the this ATM clouds. And that computational complexity is of course of this is directly proportional to the number of links. So, definitely it limits scalability, and again there is an excessive management complexity for running two separate routing protocols. On the one hand you are running the IP routing protocols, and then these virtual circuits are established using a separate ATM routing protocols. So, you have to manage both the IP routing as well as the ATM routing. And of course, the disadvantage of segmentation and reassembly overheads continues. And one more thing is that even though the ATM network supposedly provides quality of service guarantees, it is difficult to extend the quality of service guarantees to the IP world. Okay. So, even if the underlying network is capable of providing quality of service guarantees, it does not really matter, because those QoS which is available at the link layer cannot be extended to the IP layer, because IP is not supporting any quality of service guarantee. So, therefore, the QoS advantages of the ATM are also not there by using this overlay paradigm. So, basically the question then is that what are basically we are looking for. What we want really is that we want the scalability, flexibility and robustness which is very similar to the IP world. Okay. So, that is what really we want, that it should be scalable or flexible just like the IP world. So, we want to retain all the advantages of the internet on the one hand. On the other hand, what really we want is that in the core of the network, we do not want a hop by hop routing or something like that. We basically want that IP packets must be forwarded based on virtual circuits. Okay. So, what we should do is that in the ingress of the core networks, we should aggregate those IP packets into a virtual circuit, put bundle them into some virtual circuits, and then do the forwarding based on these virtual circuit numbers or something like that. So, what does it mean really is that we would like to have an not an ATM switch. It should not segment those IP packets into ATM cells and then reassemble those ATM cells into IP packets. It should not go into these segmentation and reassembly overheads. It would have been quite good if these ATM switches, instead of working on the ATM cells, are directly working on the IP packets themselves. So, what really we are looking for is that we would like to see that if ATM like switches, if they start participating in the IP routing itself and in the core set up the routes based on something similar to virtual circuits only, then we will have what is called as label switching paradigm, right. So, that leads to label switching paradigm. So, that gives a birth of label switching paradigm. The important ingredient of a label switching paradigm is that it integrates the label switching with the network layer routings. Okay. So, if I say that let ATM switches sort of participate in the IP routing, then we would would have developed some kind of a label switching. So, what we want really is that our goal is that we would like to improve the network layer scalability. Okay. So, the network layer scalability should be similar to the IP world. Okay. That is what we are looking for. We want high speed scalable switching. So, in the core we do not want the disadvantages disadvantages associated with longest prefix match basically, and we would also like to have the traffic engineering capabilities in the IP world. So, if you integrate the label based switching with the network layer routing, then we basically have what we call as the label switch routers. Okay. So historically, however, if I see the birth of label switch router actually arose from the difficulties that were associated with the longest prefix match. Okay. So what was envisaged that instead of looking up the destination IP address and do the longest prefix match, if we could attach some kind of a label with an another shim header, and if we could attach a label just like in the ATM world, where you are doing the switching based on virtual circuit identifier or virtual path identifier and not based on ATM addresses. Okay. So if you can do that, so what we do is that you set up a label switch path and then do the forwarding based on this label, and this the length of this label should be small, so that a direct index lookup is manageable and possible. Okay. So instead of having 32-bit IP address, we can have a 16-bit label or 20-bit label, so that the number of entries in the table would be of the order of 2 raised to power 20 or 2 raised to power 16 and not as high as 2 raised to power 32. Then a direct index lookup is possible, and as a result the problems that are associated with the longest prefix match that will go away. So just like similar to the ATM world. So originally the idea was that you could attach some kind of a label and then do the high speed switching based on this label, but slowly it was found that when many forwarding algorithms were proposed in the literature for high speed forwarding, it was soon discovered that actually speaking the IP address lookup problem can be addressed by the modern algorithms, and the real advantage of the label switching paradigm lies in addressing the traffic engineering challenges that exist in the IP world. So let us see what are the key features of these label switching paradigm. Now the key features of this label switching paradigm are that just like in the ATM world, a path is basically established between two endpoints. Okay. This is like a virtual circuit path. Now at the ingress of the network, packets are partitioned into forwarding equivalence classes. Okay. Now, so this is a concept that has been introduced. I will just elaborate on this. So what you basically do is that you want to determine how you want to set up a path between two endpoints. So suppose you want to set up a path between two endpoints with certain bandwidth guarantees. Then what you do is that at the ingress you partition the packets into forwarding equivalence class. Now each of these forwarding equivalence class may have a certain quality of service attributes associated with it. Okay. So at the very coarse level, a forwarding equivalence class may be associated with a destination IP address prefix, okay, an IP address prefix. That means you are doing the routing just based on IP address prefix. Okay, that is at the coarse level. At the finest level, your forwarding equivalence class may be associated with an application layer flow. Okay, so therefore you may classify the packets into different flows also and set up a path for each forwarding equivalence class, or set up a path for each application flow. Okay. Now what you will do is that then each of these forwarding equivalence class you will associate it with a label. Okay. At the ingress the packet will be tagged with a label. Okay. So at the ingress the packet is tagged with a label, and then the label will be used rather than the IP address in the core. The label then will be used to determine the next hop and the new label. Why the new label? Because remember that we are following the label swapping paradigm. Okay. So, the old label is swapped, may or may not be swapped, but it may be swapped with a new label, and then you will determine what is the next hop over which the packet needs to be forwarded. Okay. So, there are so what does it mean at the ingress of the network you are doing multi-field packet classifications. Okay. Now, the classification rules can be determined based on your definitions of the forwarding equivalence class or the FEC rules. Okay. So, at the ingress you are doing multi-field classification of various IP packets, okay, that are coming into you into one of these forwarding equivalence classes or one of these flows. Okay. So, while the ingress routers are little more complex, okay, in terms of operations, they will require a multi-field packet classifier. They have to attach a label, okay, and then sort of forward the packets if the packets are not tagged, and if the packets are tagged, of course they will have to switch the packets based upon the tag. But on the other hand, in the core of the networks, the label switch routers are very simple. They just look at the tag and then do an index lookup and determine on which hop the packet needs to be forwarded. So, the core is very simple. So, we have a label switch router, what is called as an LSR, which is basically a core router, and we have a label edge router, LER, which is situated at the ingress of the network. Okay. So, LER is at the ingress of the networks, LSR is in the core of the networks, or what is called as label switch router. So, label switch networks then looks something like this. So, remember that here in the core of the networks we were earlier having an ATM switch. Now, instead of ATM switch we are having what is called as label switch routers, and these are all IP routers. So, you can see that these label switch routers, okay, so here your IP packets need not be segmented into the ATM switch or ATM cells or so. They are working on these label switch routers are working on the IP packets themselves. Okay. So, that is one advantage that we have, is that now you do not have to no longer work with the ATM cells, but you are directly working on the IP packets themselves. And then, like in the ATM switch, in this network of the label switch routers, you are determining a path based on certain rules or classification criteria. You are determining a forwarding, you are classifying the packets into forwarding equivalence class, and then determine a label switch path in the label switch networks. So, what is really happening is that now the IP routing is tightly integrated with your determination of a label switch path in the core of the networks, and the routers are also working on the variable length IP packets and not on the ATM cells. So, we have integrated with many of the concepts of the ATM world with the IP world, and have given rise to the concept which is called as IP label switch router, which is also called as a multi-protocol label switch routers. So, we will look into what are the various protocols and other features of MPLS later.